My name is Leandro. I work at the open source team at HuggingFace. And today I want to talk about a project I've been working on on and off probably a year now. It's CodeParrot. And what it's about is mainly about models that can generate code. So maybe let me start by asking a question like, how many of you have heard of Copilot? Like most of the people, how many have used it actually? Also quite a lot. So that's nice. So about a year ago, OpenAI released a model they called like Codex. And around that model, they released a service that's called Copilot. And what Copilot can do is you write a function, maybe you write some signature, what that function should do, and Copilot completes it for you. In many cases, it can complete like the whole function. Sometimes it just writes a single line or a larger block. Depends a little bit like how your query is. And people got like really excited about that Codex model because before there were some models that are kind of okay at code generation, but nothing was as impressive as Codex that could really generate whole methods, classes, functions, and so on. One cool thing they did in one of the demos is they showed how you can, with natural language, end-to-end program a whole computer game without needing to write a single line of code, just by like typing instructions in comments. And so the way it works is like you have a plugin in VS Code, you type things, that goes to a service that's called Copilot. Copilot is a project that GitHub and OpenAI do together. And that service is powered by Codex. So Codex is just a model where Copilot is the whole service that does like all the other things that you need to do surrounding the model. What OpenAI did is they took GPT-3, a large language model, and they fine-tuned it on like a lot of code data. So they scraped GitHub, trained the model. They just continued training for a bit, the GPT-3 model, and then they called it Codex. So Codex is just an autoregressive model. It's designed to just predict the next token or the next few tokens based on the previous tokens. And in Copilot, they do then all the things where they get some context from your editor, they pass it through the Codex model, make some predictions, and then they feed you back some predictions or suggestions that you can use. And they can also use that service to then improve the model itself by seeing like which of the suggestion that the model made you actually used. So that's really exciting. A lot of people are using it. But that was just the beginning. Like Codex was released a year ago, and since then, like already like a lot of things had happened. One thing is like the competition didn't sleep. So people thought like, oh, if GitHub can do Copilot, I mean, Amazon thought we also have compute, we also know how to deal with data. So we built like Code Whisperer. It's a very similar product that they released a couple of months ago. Another very interesting model in that space is AlphaCode. AlphaCode is a model that DeepMind built, and the idea is very similar to Codex. So it gets some text or some code, and it can continue the generation. One thing that's a little bit different to Codex is kind of like a general purpose model. So it can write classes, it can write functions or docstrings, whatever. AlphaCode is specifically designed to be really good at competitive programming. So they first built a model that's very similar to Codex, but then they heavily optimized it for code generation in the competitive domain. So I don't know, how many of you know LeetCode or like LeetCode challenges? Like most of you, it's like these platforms where you get a task, right? I don't know, a function that filters a list or sorts a list, something like that. And then you have to write a function. And they trained their model on a similar data set. And they showed that on a website or like a platform called Codeforces, they beat like 54%, or they're in the 54% of participants. So it's not fully competitive yet. It doesn't beat like the best competitive programmer, but it's like very decent. Just a couple of weeks ago, Google, in a similar space, Google released a blog post where they discuss a little bit of a tool they developed internally. It's not Codex, it's a little bit different. They use a much smaller model combined with more classic approaches like semantic engines. These are like the autocomplete functions that you used like before language models were a thing. So they combined like the best of two worlds. They built a tiny transform model with that combined with that semantic engines, and they rolled it out internally. And they looked like, how do programmers work with these tools? And what they found is like, they have roughly a 6% reduction of the time it takes people to run the tests again. So they, in a sense, like how long does it take them to do a single iteration in coding? 6% might not sound like that much, but if you think about like Google has like 10,000 programmers. If they're 6% more productive, that's like 600 people that you got for free, in a sense, with like a very tiny model. And they also say like that currently about 3% of the code that goes into the code base was generated by that model. So that's also like a substantial amount of information that goes back into the code base. So that's nice. If you're anything like me, probably you want to test these models. But if you ask these like big tech companies, none of the models I talked about are open source. So Codex, there's a paper around it describing it a little bit. But the paper is about a model for Python. But if you use CodeParrot, you notice it can do more than Python. So obviously they did more stuff. CodeWhisperer is the same. Like they didn't release any model. They didn't even release like a paper or anything. And same for AlphaCode. So there's a paper. There's, I think, even a web demo where you can play a little bit with it. But there's no model that you can use. So what I want to talk about today, that was just like a quick introduction into the tools that exist and what people have been working on. I want to talk about two things, like how we trained CodeParrot. So how can you build like your own Codex model? And maybe in the end, a little bit like, where can we go next? Maybe just like doing these CodeParrot things is not enough. You want to go a step further, and I want to explore some ideas. So to show like the state a little bit more in detail, I made like a rough timeline. It's not very a strict timeline, so it's not axis, not a time axis, but it shows you a little bit like how the field evolved. Like at the very beginning, you had these small models. Then last year, Codex was released. On the y-axis, you see like the size of the model. So Codex has about 10 billion parameters, whereas like the largest model before had like a few 100 million. A few months after that, Google released a model. They didn't even give it a name. It's just called like the Austin 21 model, because Austin was like the first author of the paper. It's a really large model. It has like 130 billion parameters. And it's essentially like a model they've developed. I think it was called Flan, which is like a natural language model. And they also fine-tuned it a bit on code. And they showed like how good that can code. And AlphaCode is like a 40 billion parameter model. So if you look at the colors, all the red ones, they aren't released. So you can't access them. Since then, the field has a little bit improved. Here's CodeParrot. There's other work by CMU called the Polycoder, which is like a 2 billion parameter model. And recently, Salesforce released CodeGen, which is very similar to Codex, and Facebook has released Encoder, which is slightly smaller, but it can do other cool things like infilling. But when we started, that was pretty much like the state. So these models were released maybe in paper form, but they didn't release the data. So if you wanted to train a similar model, you have to first get some data somehow. There's no code, so you have to write your own code base. And there's no model, so you can't even fine-tune it if you don't know how to pre-train. So that's a little bit sad. Sad for many reasons, actually. Like sad for people like me or you who just want to like play with these models and see what they can do. But also sad for researchers, right? Because maybe you have like a cool research idea that builds on top of Codex. And if you want to do that, you have to retrain a Codex model just to explore your ideas, which is also not that cheap to do. So maybe you burn your whole like compute just to get to the state where OpenAI was a year ago. So we thought, let's improve like that state a little bit. Like HuggingFace is an open source company, so we try to do things open source. Our main like motivation was less like building a model that's competitive with Codex. I mean, you need to go pretty large and you need to train for a long time until you get there. But we wanted to show like it's possible and mainly release the data and the code. So anybody can, maybe if you have more compute, you can train larger models and you wouldn't need to start from scratch again.
So by the way, are there any metrics for understanding which one is I mean, how good is each model?
Yeah, so that's actually a good point. You can ask me questions anytime. You don't need to wait for the end. So Codex is like, that was the best model, and everybody tried to like beat Codex or be as good as Codex. So these two models, I think they didn't compare to Codex to the same benchmark, but CodeGen and Encoder, they compared against it. And CodeGen essentially is as good as Codex, and Encoder is a little bit worse. I'll talk a little bit later about like a few benchmarks that people are using. A common one is, for example, human eval, which is where most of the models nowadays are evaluated on.
Another question?
Yeah.
Where are you getting data from? Like GitHub has a lot of data, and the CodeGen.
Yeah.
Where they?
They're all trained on GitHub code data, essentially.
Oh, they parsed it just. Okay.
Yeah.
That's reasonable.
Also coming to that, like in 3 slides or so. So, but before we get to the data, we need to decide like what architecture we want to train. That's like a very simple example of maybe how your corpus might look like that you want to pre-train on. You have a function, you have some docstring, and you have the body, and you want to model that somehow. In transformers, you have like different ways you can address this. Like the original transformer is an encoder-decoder architecture. So you have an input that goes into an encoder. The internal state of that encoder gets fed to a decoder that's then responsible to actually generate like a response to your input. And if you think about code, one natural way you could like structure that is like you parse all the docstrings, and that's kind of like your prompt. And then you want to generate like the code actually that belongs to that. That's a little bit like text to code translation. And these models, like if you're not in the code domain, they're usually used for like summarization or translation, these type of tasks. AlphaCode uses that architecture mainly because like the challenges they have, they're very much structured like that. You get like a natural language instruction for your programming challenge, and then you need to generate the code. And one advantage you have with like an encoder-decoder architecture is like the encoder is bidirectional. So every token that's parsed can look at all the other tokens. Whereas if you only have a decoder, you can only look at like the past ones. So that's really good if you have things like instruction that you want to go through. The other two things you can do is either mask language modeling, which is more what BERT does, or Roberta or XLMR, where you have an input and you kind of like corrupt it. Either you mask some tokens or you maybe mislabel some tokens. So you replace a class with you replace the definition with a class, or the return statement is like slightly changed, and then the task of the model is to decorrupt it, to find like the original text. And lastly, what most of these language models do, like GPT and the other code generation models I showed, is causal language modeling, where you just take like the previous context and you predict like the next few tokens or next token. And we wanted to do something similar. We also wanted to do code generation. So we went for like a decoder-only architecture. We trained a GPT-2 model, essentially like a large GPT-2 model. So now we have an architecture. We need a data set. The scaling laws predict or dictate pretty much that if you want to train a large model, you need a lot of data and a lot of compute. So first we need to get like a lot of code data. And as you already hinted, it's GitHub essentially that you use. So you want to go to GitHub. That's probably the largest place where you can get like freely accessible code. There are essentially two ways you can go about it. Either you go, you write your own like web scraper. You go to GitHub and clone every repository you find. That's probably a little bit of work. A cool thing that exists is BigQuery, and it has a lot of public data set. And one of the public data sets they have is GitHub. So they have not all of GitHub, but they have like a subset of GitHub with like certain licenses. And within like maybe 30 minutes, you can query that data set and you can create like a 160 gigabyte data set of code, of Python code. We did that. We got like 3 million repositories, and we only selected Python files because we wanted to build something similar to Codex, just to reproduce a little bit what they've been doing. But you can do much more than that. Any questions so far?
We're in full speed.
Good. So I just want to advertise a little bit like some tools we are building. One is HuggingFace datasets, and that's what we used for all the pre-processing. Probably most people who know HuggingFace have heard of transformers. That's like, I think, the most popular library. But datasets is actually a really cool library if you need to deal with like large datasets. And it works really very similar to like transformers. So if you want to load a dataset, we have like 10,000 datasets on the hub. And you can just call load dataset. It grabs the dataset from the hub and stores it locally. One thing that's really cool about datasets in the backend, it uses arrow, which means that when you use the dataset in Python, it never actually loads the whole dataset into memory. So even if you have like a terabyte large dataset and you do some parsing on it, it only takes you like 1 megabyte of RAM, which is quite cool. So that's called memory mapping. So in case you don't have like a machine with a lot of RAM, that's something very nice to do. I don't know who has used pandas to load like a few gigabyte data set. Usually it's quite a pain, it takes like a long time, and like the data set in memory is way larger than it is on disk. So datasets deals with that. Sometimes you have a data set that's larger than the disk you have if you're maybe working on your laptop. And we have a feature that's called streaming. So if you just pass like the additional argument saying like streaming true, then instead of loading the dataset first locally, it just streams samples on demand, and you can iterate your dataset without actually ever needing to store the full thing on your disk. We did some filtering. I'm going to talk a little bit later about that. Essentially, we did some deduplication, and we filtered some files based on like some heuristics, like what's the average line length, how many non-letter do you have in your file. So if there's only like numbers, maybe it's not a very good code file. We did a little bit filtering on that. And once you have that, you need to tokenize your data set. And since your data set consists of many files with different lengths, you need to somehow deal with that. So your model has like a fixed window. We went for like 1,000 tokens. You can also go for more. And you will have some samples that maybe just fit your context length, but you will also have some that are either shorter or longer. And the easy thing to do is just do padding and truncation. So the short one, you just fill it with like padding tokens. The long one, you just cut it off. But that's wasteful in two senses. In the padding sense, like you do a forward pass even on the padding token. So that's going to be using a lot of compute for nothing because you mask it out later anyway. And if you truncate it, you're going to get rid of all the file endings of long files. And one, maybe you get some kind of biased with that, and two, you get rid of data that you could potentially use. So a trick that you can do is like you tokenize, and then you concatenate like many samples with like an end of string token, and then you actually cut those. So in here, in input 2, you have a little bit of code from input from sample 1 and a little bit of sample 3. But you can train it anyway, and the model knows where to focus attention on because it has that EOS token in between. One way to speed up training is if you have many GPUs. There are several ways how you can deal with that. By far the simplest is data parallelism. So assuming your model fits into your GPU, you still might want to use like many GPUs because that speeds it up, and data parallelism essentially helps you do that. If your model doesn't fit into your GPU, then you need to do like more fancy things like pipeline parallelism, tensor parallelism, and that's quite a bit messier than that. And the way it essentially works is like you have many workers, each worker is a GPU, you have a data loader that gets the data and then distributes parts of the batch across each worker. The worker does like a forward and backward pass on like the mini batch in a sense. Then the gradients are gathered and averaged and then sent back to each worker, and each worker updates the model. That might sound a little bit wasteful because you update the model as many times as you have workers, but if you do it on one worker, you have to distribute it after, so it's going to be slower that way. So no money wasted. And then at the end, you just repeat. You start from the beginning again. Sorry?
What's the command produced to me?
Yeah, pretty much. So what did we do? We trained two models. One we call CodeParrot Small, which is like a 100 million parameter model, and CodeParrot Large, which is a 1.5 billion parameter model. And we trained it on like the largest single machine. So we didn't want to do multi-machine training. We just want to do single machine training because it's simpler, and it's also, you don't have to deal with like latency between workers, things like that. And the largest machine that you can currently find is like a 16 GPU machine on GCP with A100s. And you can train such a model like in a few weeks. So the small CodeParrot model, we trained for like 30 billion tokens and takes a day. For the large model, it takes like 10 days. And you can also see nicely the scaling loss kicking in. So you see the blue is the loss of the small model. And you see how it flattens down, whereas like the larger model continues decreasing longer. So we see that the loss goes down, but we want to actually know if that's a good model or not. So we want to evaluate. And a common benchmark is human eval. Human eval is essentially one of these lead code type challenges where you have as an input the function signature, you have a doc string, and then the model needs to predict like the code that goes into the function. If you're like in NLP and especially in like translation task, you could look at this as like a translation task. You translate the description to like a solution. A natural thing you could do is maybe do bleu and see like what's the overlap between tokens of your generation and some reference. But that's actually a pretty bad idea, because if you think about code, you have a lot of freedom how you name your variable, how you structure your code. So the overlap between the tokens of some reference might be very different to the tokens you have in your solution. So here's just an example where you have a candidate solution. It's just like a one-line list comprehension, and the variable here is that's used is E. And you have like the reference solution, which uses X, and it uses like that intermediary variable to store the results before returning it. And like, yeah.
Yeah, it's fun, I think, but you can, if you would use C# or Java or something like that, you could just convert it into the basic language like MSIL or something like that, bytecode. Essentially, you would be able to verify.
Yeah, exactly. That was my point. Was just about to make. Like, you could parse this and like verify if this is actually functional, like equivalent. But just before I move on to the solution here, on the right-hand side, you can see like if answer is correct and the bleu score, they don't correlate very much. So you don't want to do bleu. You could do parsing, but it's kind of like a pain to do. In software engineering, you have a like much better tool, and it's like you have unit tests. So you can just write a unit test and check like, does it actually do the things I hope it does? I mean, still in unit tests, they can be like not covering everything. So maybe the model is still not doing the right thing, but actually it's fooling the unit tests. But that's one way to do it. And that's like a pretty common way now, especially in Python, because you can do it like very easily. Mm-hmm. If you just go for like kind of like accuracy, like one shot, you have one problem and a solution and you test it, that can be quite noisy because you have like a generation process in between, and some of the generations might be wrong, but if you generate like many times, you get actually like a more stable signal if the model is doing well or not. And so OpenAI created that human eval data set, and they also created a metric for that evaluation data set, and they call it like pass at K. And K is like the number of generations the model gets that are tested. And so here is like the example of K equals 3. The model gets like 3 shots at finding the right solution. You use sampling, so each generation can be a little bit different. Then for each one, you run the unit tests. And if any of these candidates, any of the 3 candidates pass, you consider the task to be solved. And that's also a nice metric. For example, if you want to do suggestions and you give like 3 suggestions in Copilot, then pass a K is like a better metric because it tells you like, what's the chance if I provide the user with 3 generations that one of them is like a good one? One thing, just like a minor thing they do, they estimate that a little bit like statistically. So if you want to estimate pass at, for example, 100, they do 200 generations, and then they see that you can like compute what's the probability if you sample from those 200, that if you sample 100 from 200, that like one correct solution is in there, and that makes it even more robust. And here are some results. That's a little bit of big tables.
How do you generate these unit tests?
They're part of like the data set. One thing that's interesting is like they thought about like how, when they release Codex, how can we test it? There are some benchmarks, but those benchmarks are also on GitHub. So maybe you already trained on them. And so the way human eval was constructed is by manually creating new problems and unit tests. One thing to note about human eval, it has like 160 samples, so it's not a huge data set to test on. And I'm gonna come back to that a little bit later. So yeah, here is what we, some results. Polycoder is like that also smallish model that Carnegie Mellon University released a few months after us. GPT-Neo and GPT-J are like general purpose GPT-3 models. They're like open source versions of GPT that Eleuther AI built. And then you have Codex. And you can also see like the number of tokens these models were trained on. There's a star with Codex because Codex was initialized from GPT-3, so it was actually trained on 300 billion tokens more than that. And you can see like we're still in the small data, small compute domain. We trained on much less than these other models did. Polycoder is kind of similar, but on similar amount of tokens, we're pretty much on the same level or a little bit better. But yeah, if you really want to beat Codex, you need to train a little bit longer, and you also need to scale a little bit more. They have like larger models, but you can see we're on the right track. Yeah.
And ask, so on the right side, you show the share of Python tokens.
Yeah.
The columns on the left for pass at whatever, pass at k, are they only for Python unit tests or different? Okay.
Yeah. So human eval.
In the bottom rows.
Sorry?
Even in the bottom rows, like GPT-Neo and Codex, which saw other languages as well, they were evaluated just in Python.
Yeah. Codex actually, the Codex version in paper was only trained on Python, and that's the numbers they reported. But GPT, yeah.
The higher is better or the lowest?
Yeah. So pass at 2% means if you generate 1, there's a 2% chance that you generated like the correct solution. And if pass at 100 is 17%, that means if you generate 100 samples, there's a 17% chance that the correct solution is among those. So you can see like the largest Codex model is like quite a bit better than all the other models. And you can also see here like the Python and code token. So for Codex it's the same. So they were only, these models at least were only trained on Python code. Good. I just wanted to show like a few demos. Like obviously, like the models that we trained, they're not competitive Codex models, but you can still do cool things with them. One thing that you can do, for example, is you can use the model and do some highlighting on your code. We did like just some demos internally. Not only internally, we also like open source them and put them on the hub. But what you can see is like you can find kind of bugs or things that are surprising to the model by visualizing like the probability of the model for each token. For an autoregressive model, that doesn't work perfectly because it gets constantly surprised because it doesn't see the future. So for example, when you have imports, there's no way the model can know what you need to import because it doesn't see the rest, right? So those are not the perfect choice, but we did some cases where you have like a bug in there and you can see it like highlighted, and that's probably like one interesting thing that you can do with like a bigger model and maybe like an encoder model. Another thing that Codex and Copilot recently introduced is like a code explanation tool. So you can select a piece of code and it writes some natural text what that code does. And we did just like a proof of concept where we want to see, can we bootstrap something like that ourselves? And so we went back to BigQuery. We got like, I don't know, like 200,000 Jupyter notebooks, and we parsed them. So a lot of Jupyter notebooks have kind of like that structure, right? Where you have some markdown, some code, some markdown, some code. And we thought maybe we can, if we clean that up a little bit, we can get like some decent code explanations. So we filtered that a little bit to see like the notebooks that have actually some text in them and then have like a decent amount of text in them. And then we flipped like the order of the markdown and the code pairwise. So instead of having the description first, we have the description second. And it's not ideal, but at least you can see that if you would get something like that from a code like that, it's like a start of an explanation. And if you have some more money or some people to actually hand label a little bit of data, you could build something like code explanation. And that's pretty much how it looks like. Here's like a scikit-learn example where you do test train split. I mean, it's super simple, but you can see then the code generates, the model then generates like a small description of what that is. We've open sourced like all the data sets we used, all the code and all the models that we trained in an organization called CodeParrot. There's also code generation with HuggingFace, which is a cool interactive block one of our coworkers built, where you can play with encoder, CodeGen, and CodeParrot and see how they generate like differently. A few learnings. Obviously, like if you ever worked in industry, that's probably like the most obvious statement you can put there, but data quality matters a lot. We had at the beginning like an issue with the pre-processing pipeline, so there were duplicates in the data. We did some cleaning, but there was duplication. And just by removing like exact matches, so if two code examples are exactly the same and removing one of them, you get like a huge increase in that poset K metric. So you see it's like 70 or 50% that you get just by deep duplicating the data set. We're now doing more experiments with near match deduplication. So a lot of config files are almost always structured the same way, but they have like some small things that change. And we see that doing these things improves things further. But that's kind of work in progress. Oh, somehow DE traveled down. That's accelerate. We use two framework.
It's fine. It's accelerated, you know.
Yeah, DE is too fast. We use two frameworks. One, again, like a framework that we developed that's called HuggingFace Accelerate. And with that Accelerate, you can pretty much write like native PyTorch code. You don't need to change too much about your code structure, only like maybe 5 lines of code in your whole script. And by doing that, you can easily run your code on CPUs, GPUs, TPUs, multi-GPUs, multi-machine, multi-GPUs, and so on. And you can also use things like deep speed. So it's very flexible. So if you can write PyTorch code, you can do whatever you want. So that's super nice. There's another framework called Megatron LM that NVIDIA developed, and it's much more complex. It's heavily optimized for GPT kind models. I mean, officially for transformer models, but it's really good for GPT models. And it's very complex. So if you want to know how you do things in Megatron, you go to the code base and it's like a pretty overwhelming beast. But if you go through the effort of actually setting it up, we saw like up to a 2 times improvement in speed, which is mostly due to like for training. I think there's now like a deep speed inference thing that also helps you up like to inference speedups, but just for like training. And especially if you do like very long trainings, a factor of 2 is pretty significant. If you just do fine tuning for an hour, then probably you don't care about setting up Megatron. But yeah, if you do pre-training, it's significant. But you also need to do conversion. So if you later want to use the model again in transformers, you need to run it through a script. So there's a little bit more involved with that, and yeah, kind of a trade-off between the two. So I talked about CodeParrot. I want to switch gears a little bit and just do like a side note about Bloom. Bloom, who has heard of Bloom and Big Science? Like a few people, less than people that heard about HuggingFace. So Bloom is like an open source project. Big Science is an open science project that we started at HuggingFace, but it's like an open collaboration. I think in the end, people from over 60 countries participated in Big Science, and the goal was, can we train something like GPT-3, but in the open? Because again, you have that problem. Nobody knows like all the dark magic that went into training GPT-3. People don't have access to it. People don't know what data was used. So we wanted to build like an open version of that. So it's like an open collaboration. One goal was also to build a multilingual model. So Bloom can talk in 59 languages. And it was trained on a public cluster. It's like Jeancey, it's a cluster by the French government, and it has like 400 A100 GPUs that we could use. And so to train that 175 billion parameter model, they ran on those 400 GPUs for, I think, 100 days. So a bit more than 3 months. So why am I talking about this? One cool thing is Bloom was trained on 10% code. So part of those 59 languages, I think 13 of those are programming languages that we sneaked in. So 10% of the code is data. Of the data is code. And one thing that's pretty cool, it's really good at coding. So 10% corresponds to about 30 billion tokens of code that it has seen. And it is as good as like the 2 billion parameter codex model. So it's pretty decent. But one fun thing that you can do, because it's multilingual, here's like an Arabic description of writing a factorial function. And then the model generates like the function for you, which I thought is like kind of a cool application, especially for like people who don't know how to program and maybe don't know English so well. So you can do cool things with it. So where to next is with that, do we have all the code, all the data, and all the evaluations that we need? No, I mean, there's still some challenges. Like if you look at all the papers, Codex, AlphaCode, CodeGen, and Encoder, those are essentially all the passages that explain how the data set was created. And you don't need to read through it. I can give you like the summary. They all went to GitHub. They all did some filtering. They all filtered for some licenses, but they don't release it. So you don't know exactly what kind of filtering they did. You don't know what kind of licenses they used, which is like a pretty important thing if you want to build like commercial applications. You don't want to generate commercial code, which has happened, I think, at the very beginning of Codex. They generated like Doom source code, which people were not too happy about. So yeah, I mean, so everybody who wants to redo that, I mean, we have like the Python data set, but they usually train also like on other languages. We released a data set that's called Github-code, and it's about 1 terabyte of code data. And besides like the very frequent models, languages that are used like Java, C, and JavaScript and Python, we also tried to include some more exotic things like Docker files, Haskell, or assembly, because we thought like if somebody wants to train a language model to build to write Docker files, that would be pretty cool, and we want to give like people the tools to do that.
Yeah, it's also potentially very dangerous.
Yeah, yeah. I mean, there's also Bash files, I think so. But I mean, those are from BigQuery, so people could get them very easily anyway. We make them available through datasets, so you can stream the whole dataset, the 1 terabyte dataset. But that's only like the first step. I think there's still a lot on the table when it comes to like the data you train these models on. Just the source code is one thing. There's also Stack Overflow that could be interesting, where you have more text or questions and solutions. People at this point like mostly ignore commits. So like on GitHub, you have tons of commits, issues, pull requests, which have a lot of useful information in them that you could potentially also use. So that's not the end of the line yet.
And what was the red and blue colors to denote?
So blue is file count. So you see that's like 10 million. So you have like 20 million Java files, and in volume, they're like 200 gigabytes. So it's always 2 bars per language. One is like the size and one is the number of files. You also see like that the ratio is kind of different. Some languages have like shorter files, some have longer files. Another very like open question is like evaluation. If you compare like the state of code models to like the state of NLP in general, I think people would have been pretty upset if we released Bloom and it was evaluated on 100 samples for IMDb. People said maybe you should do a little bit more, but that's pretty much what currently happens like in code. Everybody evaluates on human eval, which is like these 150 samples. There are a few others like APPS and MBPP. They're very similar in style. They're also like descriptions of code files, of coding challenges. And they're all pretty much in Python. I mean, there are some other benchmarks, but people rarely report on them. And yeah, it's all this LeetCode type thing. So some goals that we could have is like go multilingual. I mean, I would also want to know how good the model is in Java and other languages. So even just translating some of these benchmarks to other languages will be valuable. But then also go beyond like these tasks. Like I think LeetCode type evaluations are cool because it's like intellectually impressive if you can see a language model that generates like a complicated function based on a description, but it's not like the everyday coding experience. At least I don't do that very often. So it would be cool if there were other tasks like write a whole class, which is something I do more often than like a complicated function, or set up unit tests or look at bugs, things like that. Yeah. So evaluation, I think, could use a lot of improvement, and there's a lot of work to be done. And then lastly, inference speed is pretty crucial if you build these models. Usually you look at it like a little bit after the fact. You train a GPT model, and then you look like how you can make it faster. I think there was a blog post at some point on GitHub where they said like essentially for CodeParrot, they needed to go below 200 milliseconds, otherwise like the user experience sucks. So you type something and you have to wait a second until you get the prediction, and maybe in that time you already typed something again, so people wouldn't use it. And 200 milliseconds for like a large language model is like pretty challenging. There are a few things that you can do. You can scale down the model. I think it's argued that in CodeParrot they don't use like the 10 billion parameter model, but a smaller version of it. Could do, for example, distillation to get there. You can use fast hardware, which is usually expensive, so you can run it on GPUs in production, but that's not for free. Can do optimizations. It's also like custom kernels can make a big difference, and graph optimizations. Or you can do architectural changes. So before you start training, you can think about, are there some tweaks that we can do to make inference faster? And for example, I think OpenAI and GPT-3, some layers are sparse, which makes things a little bit better, but there could also be many other things. So that kind of like wraps up the things I wanted to talk about. And I just wanted to do a teaser. That's something that we haven't announced yet. And maybe for the ones that didn't sleep, you might recognize like that logo a little bit. And we're planning to announce something addressing like some of the challenges I just mentioned in roughly 2 weeks. So there's a big project coming up in that space.
Okay, that's going to be tantalizing.
Yeah. So I hope everybody woke up again. Cool. So now I think we have some decent time for questions.
Yeah.
So there was a part about tokenization, which I guess leaves more options for, let's say, code generation, because when you look at the scope of a single function, generally the number of unique symbols that appear within the context of a function is very small.
Yeah.
So instead of doing, let's say, sentence piece or like subword tokenization or anything like that, you can just enumerate all the unique symbols and generate them as separate IDs. Do people do that kind of stuff?
I don't think currently they do a lot of these things. One reason why we didn't like continue training from a checkpoint is we wanted to have like a very efficient tokenizer, and usually that doesn't work so well with fine-tuning an existing model. So we trained our model on code, so it's really good at tokenizing like code type text. On the other hand, one other data point is AlphaCode, which used like a tiny tokenizer. They only have like, I think, 6,000 tokens, which is like nothing. It's like, I think GPT-3 has like 50,000 tokens. And that seems to be also working pretty well. So I think people are not so concerned about efficient tokenization at this point. We mainly did it for like...
I'm asking from the perspective of more correct programs, because like, you reason about them on the symbolical level, not the level of, say, characters.
Yeah, I mean, I could see like improvements, especially if you deal with like small models that are not so well, so you help them a little bit. But I feel like for the large models, usually when they're wrong, they're not wrong because they defined a variable and then they mistyped it a little bit later on. They're pretty good at like copying stuff from the past. So I would expect like the difference is a little bit smaller for like really large models, but yeah.
If I may follow up on the question that you had, so there's a lot of opportunity left on the table for, let's say, generation of not the source code, but let's say the bytecode, the assembly, or the at least LVMIR as an intermediate representation. It will also have like a sequential nature to it.
Yeah.
You can still run unit tests on it, but it will be universal across the languages.
Yeah.
It would be far more efficient, more portable. So are people trying to do this or not yet?
I don't think yet. It could very well be that I think they did it more in the past. So I think like there's a more general trend in NLP or like in machine learning even in general, like kind of following up the bitter lessons where if your models don't work well, you try to help them by doing these kind of things. But as you get like more compute and more data, usually like feature engineering doesn't help that much anymore. So if you can just get more data or more or larger models and more compute, you can kind of like make up for not handcrafting rules. But it could very well be at some point that people realize like if you want to get like the last mile, maybe we need to do something like that again. Sure. Yes?
My question is about the datasets.
Mm-hmm.
For example, this particular dataset about the code generation. Do you provide the already pre-deduplicated dataset or just raw dataset?
We provide like several datasets. The main one, that GitHub-code one, the unprocessed one, we left it as unprocessed as possible to give people the opportunity to explore their own filtering. So what we did is exact match deduplication. And I think we used like one heuristics for the maximum line length. So sometimes you have files that have like super long strings and they're like auto-generated. So we removed those. But besides that, we purposely left it as much as it is, such that we don't limit you in what you want to do. Maybe you don't agree with our filters. But I think we have one more data set where we did like near deduplication. Usually when we do something like that, we just also put it on the hub. And so people can also use it.
Yeah, but continuing on that question, don't you think that providing also your version would be like more in the direction of like replicating your research or continuing that version?
Yeah.
Maybe it can be provided with a flag. Just
oh yeah, I mean, on that data set we don't, but also because we haven't trained a model yet on that data set. We have like a Python-only data set, and there we have like all the code and the data sets available, so you can reproduce it by just running the script. So we have those data sets. We did release those. Yeah. Yes?
I need to ask about the question about the training test set contamination, like for the evaluation, like the product of course, a lot of people put their solution to CodeParrot, like you probably can Google most of the solutions.
Yeah.
And a lot of like easy competitive programming programs are very similar. It's like do something with array or something.
Yeah.
So do you address that in the preprocessing or?
Yeah. So for human eval, as I said, like that was a data set specifically created like a year ago to not have it like in the GitHub dumps. For the larger project I mentioned, we want to look at that like there are like many data sets, so you need to do a lot of decontamination of the large data set, so it's pretty expensive, but that's definitely something you want to do. Even now, we're not 100% sure if human eval is not somewhere like in a newer data set. Because if you not make a GitHub scrape now, it could very well be that somebody uploaded it, so yeah.
I'm sorry for asking this question by interrupting the audience. I just thought that, do you guys think about using something like static code verification for languages which supported like, I don't know, C++, C#, Java, and so on?
Yeah, not quite. We're not quite there yet. So we're still very Python centric, but we want to like go a little beyond Python, and there we could do things like that, but we haven't done anything yet. Mm-hmm. Also, that big project, like a lot of it is like very open to like, we want to see what people find interesting and then maybe do something along those lines. Yeah, sure.
Okay.
Yeah.
We don't have access to codecs and to
dataset and architectures, but we do have access to its API.
Yeah.
Didn't you think about distillation and all of codecs? That's it. Probably using like active learning and looking at examples where you usually give incorrect answers. So.
Yeah, I mean, there may be two comments about this to be made. One is like you need to pay codecs. It's not free, so it will also won't be free to like query it a lot of times. And the other thing is like usually when you do like distillation of some sorts, you want to have access to logits and not just to like the raw, just the text predictions, right? Because the text predictions are probably not much higher quality than if you filter like GitHub. And so you don't get, I don't think you get that information from codecs. But yeah, I mean, if you have the money, it would be interesting to try.
By the way, you use your model?
In the sense that we have it like in an editor or something? No. I mean, if you look at the performance, it's obviously much worse than codecs. And it's like, I don't think anybody would use it at this point. I think one thing that people also a little bit underestimate is like what's built on top of codecs inside Copilot. It's like they made it in a way that it's really nice to use. It's like it makes predictions at the right time. It takes in not only like the context from before, but it parses like pieces of code from your whole database. And to make that really work, it's a lot of like engineering work that goes into it. And I think if we just like have the model kind of raw, make predictions, the user experience wouldn't be that great.
In fact, it's an old story that when you want to open a project, you always have like first 99% of the project, next 99% of the rest, and then 99% of the rest, and so on. So it's a lot of work.
Yeah.
That's quite clear. Those questions on Werra.
Yeah, it's not really a question, just a comment on that last question. There was a member from the community that did create a VS Code extension that queries the hub for different code generation models, but the quality of course is quite bad. Yeah, so I think in that plugin you can essentially specify a model on the HuggingFace hub plus your API token, and then it loads that and makes predictions, and it works, but as Omar said, like it's not as good as Copilot.
You showed the table with the benchmarks on different models and also GPT-8, for example. Didn't you think about fine-tuning it or using some tricks like prompt tuning for the same task just to see what will it show comparing to your model?
Yeah, so we're planning probably to do some ablations along those lines. If you read the Codex paper, they also talk about whether it's necessary to start from a natural language model first. And they say essentially the main difference is like that the model converges faster if it was first trained on natural language, but the end performance is kind of similar. And that's what...
I mean, it is bigger than your model, objectively.
Yeah. You mean why we don't just like take that and fine tune it more?
For example, yes.
Yeah. I mean, I think that's one avenue to explore. I mean, we want to train some different models than that. It's like they're nice, but they're also not that big. So we want to go beyond that. And then the question is again, do you need to pre-train it first, or do you start directly with code? They're like, people do it differently in almost any papers, like CodeGen, the model from Salesforce, they train on natural language, on many programming languages, and then on Python. So they have like a 3-step training process, which works quite well. Other models like Encoder, I think they directly train on code, and they also get like decent performance. So I don't think people have figured out the perfect recipe yet. I mean, and as I said, like our goal here was not to beat like these models. Our goal was more, can we create the tools that you can train models like that? So, yeah. There's, I think the same community member that built the plugin tried to fine tune GPT-Neo on code. And for some reason, it didn't work at all. Like they never figured out why, but like the performance was 0 or like a few %. And so it wasn't also not that straightforward as it seems. Yeah. Yes?
So the larger models can solve more code problems. Is it your perception that they can solve harder code problems in small models?
I think so, yeah. I mean, that's also what they, in alpha code, they did a nice ablation to see like what made the model go like beyond those 50% of things. And you can see in their graph where they add like features to the model, the last few percent were like by scaling. So like if we make the models bigger, then it gets better. Yeah. Yeah.
If we see in the metrics, we see that codex, even with 300 million parameters, is much better than CodeParrot.
Yeah.
What should they do?
I mean, there.
It's several times better.
Yeah. And I mean, we see now with like some tests we did that we can match them if we have the right conditions. One thing is they trained for effectively 400 billion tokens. So they have 100 billion tokens of code, plus they have 300 billion tokens of text that they trained originally on. So in total, they trained for 400 billion tokens, and we have like 40. So
it's a matter of data.
Yeah. Yeah, we found like data cleaning and training long is essentially what gets you to 36%. Yeah.
Wait a second. If the codex was trained on GPT-3, did they change the byte-pair encoding in the beginning or not?
Only slightly. So what they did is they added a few tokens for white spaces, and they said because in Python you have a lot of white space tokenization, and they said like, I don't remember if it's only white spaces or also a few other tokens, but I think it was mainly white spaces, like a few dozen new tokens, and they continued training. And that made, I think they said like, that made tokenization 30% more effective just by adding like a few tokens that are special to code that don't appear so often in natural text.
So they only kept the main part, the main structure of that and changed. Okay.
I think even like in the normal, and usually like these language models, they have like a few dead embedding dimensions, which people can use to later add tokens to them. So I think they just reuse those, or you can, if you don't do that, you can also expand the embedding matrix, and that you can keep essentially the rest of the weights. That doesn't, and then you just learn these few tokens that you add. You learn the embeddings of those. Yeah. Yeah, you can actually in transformers, if you use the library in the tokenizer, you can say add tokens. And then it expands like the tokenizer, and it expands the model embeddings. Can do both. Done. I was shown a big cross.
I mean, actually.
If anybody wants, I have like a couple of stickers and patches that you can put on your clothes or on your phone.
Close to your heart.
Yes.
Leandro, thank you so much for coming and for giving the talk about CodeParrot. It's fantastic to get an insight on how these things could be built. And it would be very cool to see more people like you coming to year one again and again. Thank you so much.
Thanks a lot. It was a great pleasure being here. Thanks.
Thank you.
Thanks. You want to?
Yeah, of course, why not?